Good morning, everybody. Happy Monday to you all. Today we're going to continue on with 4.3. Okay. If you remember, the last thing we did in 4.3 was we did our synthetic division. In fact, on Friday, you had a chance to do some extra credit where it was just doing synthetic division on problems. Today we're going to learn about something called the remainder theorem. Okay. This remainder theorem helps us evaluate polynomials. Okay, and to do that, we are going to be using synthetic division. Let's first review what evaluating a polynomial means and how we used to, or how we have done it in the past, and how sometimes we occasionally will still have to do it. But when you're asked to evaluate a polynomial, it's going to say, hey, what's the value of this function? So here I've got a function, it's graphed. Looks like it's probably a cubic polynomial. Looks like the lead coefficient is positive. It goes up to the right here. Okay, so we know a little bit about this polynomial. And we could ask questions like, hey, if x is 0, what is the value of the polynomial? What's the function equal to? And we could just go up here to the graph. When x is 0, it looks like the function is equal to about 4. We could ask, hey, when x is 1, what's the value of the polynomial? It looks like it's about 3. When x is about, negative 0.8, the function is equal to 0. And when x is negative 1, looks like the polynomial is maybe about negative 2. So if we had a nice, beautiful graph, we could use that to evaluate the polynomial for various numbers, for various x values. However, you can see I'm having to guess a little bit and make approximations. So the graphing method not super accurate without using a computer or a graphing calculator. So today we're going to look at how we can do this using synthetic division. First, let's look at the past way we've done it. Now, in the past, here we've got evaluate a function. Here's our function f of x equals, it's in standard form here, 2x cubed minus 3x squared, so it's x squared plus 4x to the first, and then minus 5. And the question is find the f of 2. Recall how we do this. If I want the f of 2, every place I see an x, I replace it with a 2. And every time I substitute, I'm using parentheses, keeps everything nice, and it also makes sure we get it evaluated correctly. Then we got plus 4, there's an x, so I replace my x with a 2 there. Close off my parenthesis, minus 5. So here's the setup for finding the f of 2. That's how that's read. Remember, we do not work on the left-hand side. The left-hand side's the question. The f of 2 is equal to what? And here's the answer over here. This is just not in simplest form. So let's go ahead and put it in simplest form. Okay, we're going to use order of operations here, as always. We have to take care of exponents first, parentheses, the exponents, multiplication, etc., PEMDAS. 2 cubed is 8. Oops, I forgot a squared up there. 3 times 2 squared is 4. And then our 4 times 2 minus 5. So I've taken care of my 2 exponents I had. Then we'll carry out our multiplications. So that is 16, 3 times 4 is 12, 4 times 2 is 8, minus 5. And then lastly, we'll add and subtract going from left to right. So 16 minus 12 is 4. 4 minus 8 is negative 4. Where did I go wrong here? Because that's not the answer I believe I'm supposed to get. Oh, no. 4 minus 8, that's negative 4 minus 5. I'm getting a negative 9, and I'm certain that's not the answer. Let me double check up here. It's 8, 3, 16, negative 12. Oops, that's a plus 8. Right there. There we go. That'll help us out. Make sure we do our math correctly here. So 4 plus 8 is 12 minus 5, and we get 7. And so we would state the f of 2 is equal to 7. Okay? And you can see that we get this nice triangle going down our inverted triangle, simplifying f of 2 from this complicated expression down to this final single number in this case. F of 2 is 7. Now, I'm going to show you something that is much easier than this using the remainder theorem. And I'm going to use the same polynomial, okay? And you'll see that on the next slide. But when I use this polynomial, I'm going to do something a little bit different with it, but you'll see that I still get the number 7. So the question is now in this case, take f of x, divide it by x minus 2. And we've been doing these problems. So here's f of x, same function I had on the previous slide. And I'm going to divide it by x minus 2, and I'm going to use synthetic division. So we put 2 in the box. Okay, remember always the opposite sign of what's right there. We write down our coefficients. We're in standard form. We've got all our terms, so we're in good shape. And we drop the 2, remember. We multiply right here. That gives us 4. We add. We multiply again, 2 times 1. We add. We multiply 2 times 6. We get 12, and we add, and we get 7. And this is the key thing. Look at that remainder. It is 7. And it turns out that is exactly what the f of 2 was equal to. This is not a coincidence, okay? And you can see by just using synthetic division and looking at that remainder, that is much less work that I did on the previous slide where I had to substitute. Okay, I didn't have to cube anything, I didn't have to square anything, I didn't have to follow order of operations. I just did synthetic division, and the remainder told me what the f of 2 is equal to. Now this is a theorem, and this theorem is called the remainder theorem. The remainder theorem simply says that if I have a polynomial, f of x, and divide it by x minus k, okay, in our case we divide it by x minus 2, then the remainder r is equal to the f of whatever that k value is. Okay, in this case it was x minus k. So if we did synthetic division, or we could do long division as well, but long division we've seen takes forever, as just as long as it would to substitute in. So if I do synthetic with x minus k, it tells me what the f of k is. It evaluates the function for me. So in words here, it says the remainder theorem tells you that synthetic division can be used to evaluate the polynomial function. That's like find the f of 2, where we would substitute in 2 for x. So if you want to find the f of x when x is k, divide by x minus k. And the remainder will be the function evaluated. Okay, so for example, if I want the f of 3, I would want to divide by x minus 3. If I want the f of negative 4, I'd have to divide by x plus 4. Okay? However, and I think it's important to understand that part, but in practical uses, it means when you do synthetic division, you just use a 3 in the box, you just use a negative 4 in the box, because remember, when we do synthetic, we always want the opposite sign. So if I want the f of 3, I use a 3 in my synthetic division. If I want the f of negative 4, I use a negative 4 in my synthetic division. Let's look at a couple of examples, and then we'll get you on your way. Okay, our first example here, we've got this polynomial f of x. This is different than the f of x we were using, so it's another function. Okay, it's in standard form, x cubed, x squared, x to the first constant. It wants me to find the f of negative 4. It just means what's the value of the function when x is negative 4. So you could go through and put a negative 4 in for all of these x's, follow order of operations, and simplify. But instead, we're going to use this remainder theorem, which says if I put that negative 4 in my division box. Now remember, this means I'm dividing by x plus 4. Okay? because x plus 4, I'd have to use the opposite sign. But I just use whatever I want to evaluate the function at. I write down my coefficients, 13 and 29. Strike a line, bring down to 5. Multiply, add, multiply. Oh my, this is getting pretty big. 97. Multiply, let's see here, that's 28. Carry my 2. 36. 388. I think that's 388. I gotta let my dog out real quick. Of course, she'd want to be outside right in the middle of a video. And then I gotta do 388, negative 388, minus that 29, or reverse that. Looks like I get negative 359. Pretty big number, but that's all I want. I just want that remainder. This tells me the f of negative 4 is equal to negative 359. The same number I'd have gotten had I plugged in that negative 4 in for all of these x's. Much quicker. I did have to get out my calculator a little bit just to do some additions and multiplications, but that's it. Last example. All right, now last example, this is how your homework will look. Here's a function, semicolon, x equals 2. It just means find the value of the function when x is 2. And again, we're just going to use synthetic division. So we put a 2 in our synthetic division box. 5, 2, negative, ooh, there's no x squareds. I better put a 0 in there. Got to be careful of that. See, it went x to the 4th, x cubed, but there was no x squared, so I put in 0x squareds. Then I've got my minus 20 and my minus 6. Skip a line, draw a line, and let's go through it. Drop a 5, multiply, add. Multiply and add. Multiply, that's 48, and add, so that's 28. Multiply, 2 times 28 is 56. Add those, 50. There's my remainder. The f of 2 is equal to 50. Make sure you write that down at the very end, because it doesn't make sense if you just do this synthetic division and leave it like this. Okay, you need to write the f of 2, because that's what we wanted to find, is equal to 50. So I know if on this graph, if I was trying to graph this thing, I'd say, well, at 2, it goes way up here to 50. I don't know anything else about it, really. Except I do know it's even. I know this is a positive coefficient, so it's gonna go up here, and it'll go up here on this side probably somewhere. Maybe. I don't know where the vertex is. I just know it does pass through that point. Okay? And so that's it. All you gotta do is some synthetic division problems, and then write down the fact that you found the value of the function when f is 2.